Hi, welcome to your tutorial on applied arc length. We're going to be looking at exercise 1J, problems 2, 3, and 4. These are the three problems that you told me were difficult, so let's take a look. So first of all, in all these problems, we're focusing on arc length. Here's our formula. Arc length is the length of a portion of the circumference of a circle, and we know what portion of the circle we have by knowing the angle here. The angle tells us how long this will be. So we take the whole circumference of the circle, 2 pi r, and we multiply it by the portion of 360 degrees that we have. All right, let's take a look. The first problem was a clock is circular in shape with a diameter of 25 centimeters, and we want to find the length of the arc between the markings 12 and 5. So here's a clock. The hands are on 12 and 5, so we can see there's this angle that's going to be here, and we want to know the arc length from there to there. So that's the angle we need to know. 12.5 here is the radius, because if the diameter is 25, so all the way across would be 25, so half of that is 12.5, and that is our radius. Using our arc length formula, we need to know the angle, the central angle, and the radius. So we know the radius, we don't know this angle. To find the angle, we do this calculation here, 5/12 times 360. Because to go from 12 to 5, if there's 12 little sections here in a clock, we have gone 5 of those possible 12 sections. So we have gone 5/12 of the way around this clock right here, 5/12. And 5/12 of 360 is saying we have 5/12 of this whole 360-degree angle. Notice that when you put in the formula there, these 360s here can actually cancel. We have this 360 and then we have that one there. Cancel those, and we just end up with 5/12 times this portion. And that makes sense also because when we are doing this calculation in the arc length formula, we're trying to find out what portion of 360 we have. So when we cancel those, we can see we have 5/12. That is our portion of the whole circle. And that makes sense. We just talked about why this is 5/12. So that is our portion of the whole circle, 5/12. So 5/12, the circumference, will give us the length of this arc. And that works out to 32.7 centimeters. Next problem. We have the London Eye, Ferris wheel in London, and we are given, it has a diameter of 120, so I'm going to put that in there. If the diameter is 120 meters, then the radius must be 60. It says the passenger capsules, those little capsules there, are attached to the circumference. That makes sense. And the wheel rotates 26 centimeters per second. So imagine it turning 26 centimeters per second. All right, part A, the length of the passenger capsule would travel if the wheel makes a rotation of 200. So I've already kind of marked that angle. There's an angle of 200. If you had a line straight down the diameter, that would be 180, right? We're a little bit more than 180, so we're 200 right here. It's a big angle, and we want to know the length the capsule travels. So if one capsule starts here and follows this arc here, how far has it gone? So we're going to use the arc length formula. We know the angle is 200, we know the radius. So we put in the angle of 200, we put the radius of 60 meters, and that arc length here will be the length traveled by one capsule. That works out to 209 meters. Part B, we want to know the time it takes for the capsule to travel that 200 degrees. So we already know the distance it's traveled, and over here we know the speed the capsules are traveling. So if this capsule has to travel 209 meters and it travels 26 centimeters per second, we can convert the 209 meters to centimeters. 209 meters times 100 gives us 20,900 centimeters. Now we know the capsule has traveled that many centimeters, and we know it takes 1 second for this many. So we're going to divide this number by 26, and we're going to see basically how many seconds that is, because if we take the whole distance divided by this 26, we find out that's 803 seconds, because it's 803 of these are in that. That's a lot of seconds, but the answer is supposed to be given in minutes, so we take this number divided by 60, because there's 60 seconds in a minute, and that gives us here 13.4 minutes. Now looking at part C, we want to know the time it would take for the capsule to do the full rotation or full revolution. So not just this 200, which we just found out takes 13 minutes. How long will it take to go the whole way around? So you could do this all by figuring out the arc length again and 360 degrees and all this, but here's an easier approach. I'm going to take 360 and divide by 200. So I'm doing the whole rotation divided by 200. So basically I'm saying how many of these 200 portions are in 360, and I find out 1.8. That means 200 and then almost another 200 makes 360, right? Because 200 and 200 make 400, but since we need 360, it's only 1.8 200ths. So it's 1 200 and then 0.8 of a 200. And then we can take that number and multiply by, we know this took 13.4 minutes, and we know now that all the way around is 1.8 that far. So 1.8 times the 13.4 minutes will tell us how much it takes to finish it off. 24.1 minutes to go all the way around. Okay, last problem here. We have a door with a width of 4 meters 20 centimeters, or 4.2 meters, has an arc as shown. So this is the door here, I guess. And you can see when the door swings, it has this arc here. It says find the radius of the arc. So here's the arc. The radius of that arc would be this line right here, which is the same as this one. So that's the radius. We know, first of all, that this is 4.2, so this little portion would be 2.1. And the reason I drew this in is because now we can see we have a right triangle here. And if we want to find this radius, which I'm going to label R, we can use the right triangle. So far, there's only one side known, so we cannot use the Pythagorean theorem. But if we know an angle, perhaps we could use trigonometry to find this. So what angle do we know? Well, we know this one's 225 degrees. So that means the rest of this here to make 360 would be 135. So then I take 135 divided by 2, and I get 67.5. That gives me this angle right in here. Because again, this one would be 135 all the way here. So this one must be 67.5. Now we have a triangle with an angle, side, and an unknown side. Let's look at this. This is the hypotenuse. From this angle, this one is the opposite side. So we have opposite, and we want hypotenuse. Opposite and hypotenuse. Well, that's sine. So sine of that angle is opposite side 2.1 over hypotenuse, right here. To solve for r, we put the sine there, put the r there. We switch those. Solve that, and we get r equals 2.27 meters, which is 227 centimeters, because it wanted the answer in centimeters. In part B, we want the length of the arc. Well, now that we know the angle and the radius, we can use the arc length formula, because we know the angle and the radius. Now be careful here, you're not going to use the angle of 67.5, because we want this entire arc. We're going to go back to using the whole 135 degree angle, so the entire angle. Multiply by 2 pi r, there's our radius that we just found, and we get an answer of 5.36 meters. Actually, this calculation would give you 536, but that would be centimeters, and then I changed it back to meters. All right, great work. Hope that made sense. Please feel free to ask any other questions you may have.